When one looks at the vast space of the universe with its planets, stars, and galaxies, one fundamental question needs clarification. Why is there something and nothing? The puzzle deepens when we consider the symmetry of the physical laws that govern our universe, which seem to treat matter and antimatter equally. However, we find that the stars and galaxies we see are composed mostly of matter, with almost no antimatter. It makes us think about the complex forces that orchestrated the asymmetry and gave birth to the world as we perceive it. What deep mechanisms change the balance and give us a universe full of galaxies, stars, and the mystery of our own existence? Scientists have believed for centuries that the universe is eternal and unchanging, governed by immutable laws of physics. But in 1927, Belgian priest and scientist Georges Lemaitre proposed another idea. He proposed that the universe began with a large, pregnant, primordial atom that exploded to give birth to the smaller atoms we see today. Although Lemaitre's idea initially received little attention, the astronomer Edwin Hubble discovered in 1929 that the universe is not static, but is actually expanding. This revelation has led some scientists to speculate that as we rewind the history of the universe, it shrinks back into a small, dense point. Astronomer Fred Hoyle mockingly called this concept the Big Bang Theory, which was later adopted by its proponents. Skepticism continued, but in the mid-1960s, astronomers Arno Penzias and Robert Wilson encountered the cosmic microwave background radiation, the echo of the Big Bang, while trying to tune the microwave signals of the Milky Way. If the theory of the Big Bang is true, how did it cause the formation of planets, stars, and galaxies? Accurate calculations and observations with telescopes on Earth and space probes give us the best explanation. About 13.8 billion years ago, all the matter in the universe erupted from a single, infinitesimal point of singularity in a violent explosion. This expansion occurred at an amazing rate, doubling every 10 to the power of -34 seconds, creating a rapidly filling space. In a fraction of a second, gravity arose and other fundamental forces and energy transformed into particles of matter and antimatter, most of which annihilated each other. Fortunately, some of the matter survived and produced protons and neutrons within the first second. Shortly thereafter, these particles began to fuse together to form hydrogen and helium nuclei. About 300,000 years later, atoms began to form as nuclei captured electrons and filled the universe with clouds of hydrogen and helium gas. About 380,000 years after the initial explosion, the universe left behind a remnant, the cosmic microwave background radiation, which Penzias and Wilson accidentally detected. This radiation contained small fluctuations of matter that extended to cosmic scales during inflation, eventually functioning as the seeds for the formation of galaxies and galaxy clusters as we know them today. Today, when we look at the vastness of the universe, extensive observations consistently point to a unified story, despite the inherent uncertainties. Our universe is composed of matter and follows unchanging laws of physics throughout space and time. It works in the shadow of general relativity, expanding, cooling, and gravitating in a dynamic influenced by dark energy, dark matter, supplemented by normal matter, neutrinos, and radiation. In this cosmos we find galaxies, stars, planets, heavy elements, and even intelligent life, at least in one corner. These cosmic structures did not exist from the beginning, but were created during cosmic evolution, a major achievement of 20th century scientific reasoning. Scientists have reconstructed a timeline detailing how our universe went from a largely uniform and uncomplicated state of mostly hydrogen and helium to the diverse and complex universe we see today. Looking back from our present vantage point, we are faced with the question: how did each individual structure or component originate? We repeatedly investigate the origins of each ingredient and delve deeper until we reach the limit of our understanding. Yet, even in the midst of this uncertainty, we contemplate the birth of existence. Could everything we see come from nothing? Life as we know it is made up of tiny particles that make up the fabric of our reality. These particles join together into complex molecules, the building blocks of life, which are made up of even smaller units called atoms. However, Atoms did not materialize ex nihilo at the beginning of the universe, but went through a long-term process of formation. This process unfolds in the cosmic drama of the life cycles of the stars. Stars are born, live their celestial lives, and finally perish, catalyzing the creation of new materials through cataclysmic processes. These materials in turn promote the birth of successive generations of stars and continue the cosmic cycle. This complex interaction maintains the conditions necessary for planet formation and the complex chemistry necessary for life. In order for the universe to manifest itself in its current form, several key events had to occur. Gravity orchestrated the binding of groups of stars and galaxies, which required a primordial mass that gravitational forces could cut into larger structures. Dark matter played a crucial role in preventing matter from spreading during the cosmic formation. In addition, a delicate balance of different forms of matter and radiation was necessary for the formation of cosmic remnants, such as the cosmic microwave background radiation and the elementary components of galaxies. At the heart of this story is the mystery of the asymmetry of matter and antimatter. In the primordial melting pot of the early universe, matter and antimatter should exist in equal amounts. However, our cosmos consists mainly of matter. Various hypotheses try to explain this difference, including scenarios in which the normal laws of physics are temporarily discarded, creating conditions that favor the creation of matter. Prominent among these is the concept of Sphalerine interactions in the standard model of particle physics. When we consider the origins of our universe, we are faced with a profound mystery. Did the universe really come from nothing? While uncertainty remains, our continued quest for understanding continues to unravel the complex tapestry of cosmic evolution, probing the depths of existence itself. The universe begins with these profound questions that push the limits of our understanding. Dark matter, despite its elusive nature, is crucial to understanding the cosmos. Although it cannot be composed of particles described in the standard model of physics, several theories speculate about its origin. It may have formed early in the warm phase of the universe and continued through later cosmic ages. Alternatively, it may have occurred during phase transitions as the universe expanded and cooled. Other hypotheses suggest its existence as a new type of neutrino or as a consequence of gravity, which produces exceptionally heavy particles. The question arises, why does dark matter exist today when the early universe seemed to function without it? The creation of dark matter requires significant energy, which forces us to investigate. One interesting possibility stems from cosmic inflation, our leading theory of the pre-Big Bang origin of the universe. Cosmic inflation indicates that before the hot Big Bang, the universe underwent a rapid expansion phase driven by the incredibly high energy density associated with the cosmos itself. When the inflation stopped, this energy caused the formation of matter, antimatter, and radiation, which laid the foundation for the further development of the cosmos. In particular, inflation predicts certain patterns of density variation that are consistent with observation and provide strong support for its validity. However, while cosmic inflation provides a framework for understanding the universe's birth, it invites philosophical contemplation. Can we truly comprehend a state devoid of space, time, and the laws of physics? From a philosophical standpoint, we might conceive of nothingness as the absence of these fundamental elements, yet from a scientific perspective, defining nothingness becomes a complex endeavor. Scientifically, we can define nothing in various ways. As a time when something didn't exist, an empty space-time with minimal energy, or the absence of the universe and its governing laws. While certain definitions might suggest the emergence of the universe from nothingness, others pose challenges. The notion of true nothingness, devoid of space-time and physical laws, defies conventional understanding in the realm of physics. Grappling with the emergence of space-time from non-existence raises profound questions. How can space and time arise from a state lacking any definition of location or duration? The enigma deepens when we consider the origin of the laws governing the universe. Without a clear framework describing existence beyond our universe, the concept of absolute nothingness remains elusive. Ultimately, while scientific theories provide insights into the universe's origins, they also underscore the limitations of our understanding. The quest to unravel the mysteries of existence continues, pushing the boundaries of human knowledge and perception. Quantum theory opens up fascinating possibilities regarding the origin of both fields and particles, challenging conventional notions of eternity in space-time and physical laws. While certain assertions may suggest the emergence of the universe from a state of nothingness, the certainty surrounding our cosmic origins diminishes when we transcend physical constraints. Many scientists entertain the notion that the universe might have arisen from nothing, rooted in quantum theory. This idea revolves around the concept that quantum fluctuations could spontaneously generate a universe. However, lacking mathematical substantiation, this idea remains speculative. Recent breakthroughs by Dr. He and his team from the Wuhan Institute of Physics and Mathematics have made significant strides by offering the first mathematical proof that the Big Bang could stem from quantum fluctuations. Central to their breakthrough are the Wheeler-DeWitt equation and Heisenberg's uncertainty principle. The Wheeler-DeWitt equation, a cornerstone of quantum gravity, integrates quantum mechanics and general relativity, albeit without a consideration of time. Meanwhile, Heisenberg's uncertainty principle elucidates the transient nature of particles in the vacuum, wherein particles momentarily emerge from and vanish into nothingness due to random quantum fluctuations. Combining these principles, he and his team demonstrated that a tiny true vacuum bubble could rapidly expand, potentially leading